Okay. The next talk is from Dawei Zhang from the University of Science Technology, Beijing. And this talk is data travel material discovery and prediction for intelligent corrosion control. So you are welcome.
It's lunchtime, so I'll be quick. I'm from University of Science and Technology in Beijing, so sorry for really completely switching the topic from self-assembly materials to materials degradation. So the topic is data-driven materials discovery and prediction for corrosion control. So corrosion is a big problem. It costs about 3 trillion yuan every year for China with the loss. And also it has safety issue. It causes a lot of safety issues and also the environmental pollution. And with the increasing complex and harsh service environment that we're facing every day, we need to have a deeper understanding of corrosion and a real and dynamic service environment, and also make efforts accordingly to develop stronger, better, and more sustainable next generation corrosion resistant materials. But unlike other physical or chemical properties, corrosion resistance is a more complex term because it is affected by the cumulative and coupling effects of a wide range of materials factors and also environmental factors. So corrosion evaluation is actually the longest and most costly step in developing corrosion resistant materials. The two traditional corrosion evaluation methods include, for example, the outdoor exposure, the coupon exposure test, meaning that literally we have a sample, we expose them in a real service environment and taking it back after, for example, 1 year, 2 years, and even 10 years. And in the laboratories, we analyze the surface condition, the corrosion depths. But this is, you can imagine, it's really time consuming, and it's also highly costly, and it can only generate very small data sets. And more importantly, it cannot really reflect the impact of the dynamic environment on the corrosion process. And also for indoor accelerated tests like salt spray test, UV chamber, humidity test, the environmental impacts generated from these tests are monotonous, and which is also very different from the real service environment. So in order to facilitate the design or the discovery and development of corrosion resistant materials, we need to have revolution methods for corrosion evaluation. So the recent progresses on the experimental and computational technique has really substantially improved the data acquisition, the efficiency of data acquisition, and also our analytical capabilities for corrosion research. So the data-driven approaches in corrosion research can really help us understand the complex relationships between the composition, microstructure, processing, performance, and also the environmental conditions. So this will allow us to transform the traditional trial and error experience-based approaches in corrosion research to a more data-driven, intelligent technologies, so that we can have a more rapid and accurate corrosion analysis and also a more rational design of corrosion-resistant materials. So with this dream, back in 2015, our group proposed a concept called corrosion big data as a generous data-centric corrosion research framework, including data acquisition, database construction, data modeling, and data sharing platforms constructed for different industries and applications. So continuous, high quality, trustable data are the prerequisites for this data-driven research. For this, we're lucky in a way that our elder generations have really done many years, decades of efforts developing this national environmental corrosion platform, consisting of about 30 nationally certified corrosion exposure test stations, and also more than 100 test sites around China to study the degradation of materials in real atmospheric, soil, and marine water, seawater, and freshwater condition. And over the years, over decades, we have been able to accumulate about 30 million long-term corrosion data from 800 type of key materials. And this is not a big number, 30 million if you use big data, but for each data, it takes about at least 1 year to generate. So this is really treacherous for us to need to begin this kind of a data-driven corrosion research. Recognizing the limitation of the efficiency of data collection, over the past 10 years, we've been working very hard on combining corrosion monitoring test with this type of data-driven research. So we have developed our own corrosion sensors and also environmental sensors for high throughput in situ and real-time continuous monitoring of corrosion current, resistance, impedance, coating degradation, also more importantly, the coupled environmental parameters. And this is kind of a cartoon showing where these sensors are installed on bridges, and it generates corrosion data and also measure the environmental data, and it can automatically transmit it through a device just like cell phone back to our data center for analysis and also for online analysis. And for only about 5 years, we've been able to collect over 5 trillion corrosion data from exposure stations, also from real equipment and infrastructures. And once we have a lot of data, it's also quite important to establish databases. So other than this kind of a very static databases, we're also interested in developing dynamic databases. For example, these are two databases based on natural language processing and knowledge graph for more effective identification and recommendation of inhibitors and also steels. And for data mining and modeling, because corrosion is a complex term and it's affected by a lot of different factors, so we believe that corrosion data is of high dimensionality. So we kind of applied a two-step approach for data analysis. The first step is to identify the most important parameters that influences corrosion based on either correlational analysis or causality analysis. Once we have the most important factors affecting corrosion, and then we use some input and corrosion rates or corrosion current as the output to use machine learning for corrosion prediction. And depending on the type of data, depending on the applications, the type of data are different. For example, here we use data from the traditional coupon exposure tests, and we use the annual climatic parameters as the input, and the corrosion rates, annual corrosion rates or the degradation rates as the output, and you develop neural network model and could be able to draw a map like this for comparison of corrosivities in different parts of China. And for the data from the corrosion monitoring test, we can also develop model in a similar way by using instantaneous environmental parameters as the input and corrosion rates, instantaneous corrosion current as the output. And we can predict the evolution of corrosion dynamics over time. And this is very important for maintenance of infrastructures for their safety. And also, other than numerical data, we're also interested in morphological data, which also contains a lot of information on corrosion. And for this is kind of a quick example showing with computer vision, we can identify the location of the rust on the steel surface, and also the extent of the magnitude of corrosion over time, and also predict them. And for data sharing, typically we do this by just sending emails or creating an account on our website and allow the customer to download the data sets from the website. But over the past few years, we've been also working, establishing a lot of this kind of a visualized platform where the sensors are directly installed on their infrastructure equipment, so that the customers can really directly see how their materials behave or how their infrastructure degrades. And we build platforms for wind turbines, for highway, railways, and for national grids, and also for national museum. So over the years, we have been not only using data-driven approaches for corrosion prediction, but also for more effective design and screening of materials, and particularly on intelligent materials, namely self-healing coatings, corrosion reporting coatings, or multifunctional coatings. And this is kind of a general scheme summarizing in recent years what we have done on this intelligent coating, ranging from self-reporting coating that can detect early corrosion, and self-healing coating based on active corrosion inhibition, and also intrinsic self-healing coating based on reversible physical or chemical structures, and also multi-action self-healing coating that can consist of different kinds of self-healing mechanisms, and eventually multifunctional smart coating, for example, antibacterial, anti-icing. And of course, we have used a lot of, still use trial and error, traditional experimental approach for synthesis and development, but more and more frequently, we are relying on machine learning, on high throughput tests for faster pre-screening of the composition and for the prediction of the material's performance. So our work on the extrinsic self-healing coating has been largely centered on the identification of corrosion inhibitors and also their mixtures, depending on the performance requirement. And as an important components of anti-corrosion coating, corrosion inhibitors are typically evaluated by weight loss, electrochemical measurements, and also as well as theoretical calculations. But because corrosion inhibitors are typically small molecules, and there's really a large variety of small molecules that can be used as corrosion inhibitors. So really to identify the correct ones, it takes a lot of time. And here we develop a machine learning model based on 3 levels of features: atomic level, chemical bond level, molecular level, and we use these features as the input, inhibition efficiency as the output, and for the corrosion prediction. We have downloaded about 4,000 papers on corrosion inhibitors, but considering that inhibition efficiency is also depending on metal substrate, on the corrosive electrolyte. So after cleaning out the data set, for this work, we only used about 290 molecules from 116 papers to build up the model. And we convert the structures into SMILES format, which is more machine friendly to extract the atomic level feature, bond level feature, and also molecular level features. And the inhibitors we used consist of 12 different categories, and the molecular weight ranges between 100 and to 1,000, which is really a wide range considering these kind of small organic molecules. And inhibition efficiency covers from 80% to about 100% corrosion inhibition rate. On the right-hand side is a similarity analysis of the structure of corrosion inhibitors. Basically, the more evenly distributed, it shows more diverse structures, which is very important for developing a model with strong generalizing ability. In other words, if we have data here to train the model, and it's not going to be able to accurately predict molecular structures located in other region. And this is showing that this kind of a 3-level neural network model we developed outperformed conventional algorithm, and also a double layer similar model, which contain only atomic level and bond level features, meaning that corrosion inhibitors is also inhibition efficiency also depending on the molecular feature, which makes sense. And the model, we also, once the model is well trained, we also tested on recent publication and also several small molecules from our lab. It shows that the model is able to predict inhibitors outside of the training domain, which is good. We also improve the model by going 3D, by incorporating three-dimensional structures of the molecules into as the input, and also we incorporate inhibitor concentration information. So for this figure, it gives us information that with increasing molecular weight, the importance of three-dimensional structures on the accuracy of the model becomes more dominant, which makes sense because the higher the molecular weight, the more complicated the structure of the molecule is. And for this, it is showing that it can easily predict at what concentration we can show an acceptable corrosion inhibition efficiency, which is also important in a cost-saving perspective for practical applications. So the previous example, we show that we can predict virtually any organic molecule for their corrosion inhibition efficiency. But in reality, we often use multiple inhibitors to create some kind of a synergies that shows improved inhibition efficiency, but reduced the total dosage. But this kind of data is rarely reported in literatures. So to be able to massively generate a lot of data on the inhibitors synergy, we use this type of a printing device where the corrosion inhibitor solutions, the droplets are printed, deposited on the surface of metals. For each droplet, the concentration and also the composition of the inhibitor solutions are can be very different. And with 1 hour, we can print about 3,000 dots like this. And after letting it corrode for a while, we can analyze the surface morphology, the corrosion depths, or electrochemical signals to get an idea of the corrosion inhibition efficiency. And this is how it looks like after corrosion. And after analyzing the surface conditions, we can very easily generate a heat map like this, showing the synergy of multiple corrosion inhibitors. And this is example showing the compounding of two common inhibitor BTA and also serum nitrates. And this is a absorption type inhibitor, and this is a precipitation type inhibitor, and it has two different mechanisms. And after mixing them in a good ratio, we can really suppress the corrosion degrees very effectively. And this is showing a high throughput screening of amino acid based inhibitor mixture. And we can also use this similar technology to screen coating formulation. And this is showing that even with high viscosity resin, the composition within each droplet is still very homogeneous. And this is, and once we have this arrays of coating dots, we can immerse them for swelling, and also we can do peel-off test, and also we can do nano indentation, and also contact angle, do a lot of tests to quickly understand the composition structure performance relationship. And this is for antibacterial surface analysis and using a similar fashion. We have also used data-driven approaches for a full coating formulation design. This is an example showing we use a multi-action machine active learning and Bayesian optimization to develop multi-action self-healing coating. The coating is actually quite simple. It has 4 basic parameters, including the polyetheramine molecular weight, polyetheramine epoxy ratio, and also it is an intrinsic self-healing resin that contains hydrogen bond unit for the reversible healing of the surface scratch. And also it contains fillers that incorporates corrosion inhibitors. So for each of the 4 parameters, we set 4 different levels. So 4 to the power of 4 gives us about 256 possible combinations. And initially we prepared 32 formulations and use them as input, and the corrosion resistance of the repaired coating as the output, and train up a model using several algorithms. And we found out that random forest performed the best for this type of small data set. And then we use this model to predict the rest of the 224 formulations and generate select the top 5 and prepare them, measure them, and feedback into the input side, and do this iteratively for 6 cycles, and the model become more or less stabilized. And then we do the Bayesian optimization, which literally can give us about 10,000 formulations. We can identify the best one. This is showing the evolution of corrosion resistance of the repair coatings from the initial 32 and during the active learning, and eventually after Bayesian optimization. And this is showing the performance of the coating after 60 days of immersion in chloride solution. And basically, the best performer, once it's scratched, it quickly heals, and the performance can be the same, literally the same as the intact coating as well. And also, this is for the Salisbury test, 6 days, and nothing really occurred in the coating scratch. And finally, we have also combined this corrosion monitoring test to understand how self-healing coatings evolve over time in real surface conditions. So this is an example showing that the coating has 2 parts, basically. The resin part is a thermal-responsive shape memory polymer, which can heal surface scratch by heat. And it has a filler. It has fillers, core shell structure fillers with titanium nitride cores and mesoporosilica shells infused with corrosion inhibitors. So the titanium nitride, when their light shed on the particles, it generates heat. The heat will facilitate the diffusion of the inhibitors, and also the heat will help out with the self-healing surface scratch closure. So we made this coating, we applied them on a corrosion sensor and put them outside in a real environment. And this is what happening during the first 8 hours. And for this and this, it's a sunny period during which there is a quick rain shower. And the red curve are self-healing coating, and this is just normal coating. And we can see that during the rainfall period, the magnitude of corrosion current is much smaller than the conventional coating and more stable because, first of all, the sun will help with the surface scratch closure on the self-healing coating, and also during the rain, the inhibitors will diffuse, also suppress the corrosion on the surface. But what's more interesting was that after the rain stopped, we can see the current on the sensor with the self-healing coating quickly drops to a very low level, but it takes hours longer for the conventional coating for the current on a conventional coating to decrease. And this is because that after sun came out, it generates heat and it quickly evaporates the solution stored in the coating scratch. But for conventional coating, there's no heating, no scratch closure, and this is a wide open scratch. It takes longer for water to evaporate, so that's why it takes longer time for coating to heal, to corrosion to be suppressed. So this is already showing that with this kind of very high throughput and very frequent data acquisition, we can understand how self-healing actions occurred in real environment. And this is another example showing the self-healing coating immersed under immersed condition, how it heals and how it degrades over time. And of course, we have also combined machine learning to process the data from the corrosion monitoring test on self-healing coatings, and we can identify what environmental parameters will give the best self-healing actions, and also we can predict the service life of the self-healing coatings in real environment. And this is really a collaboration of a large team, and thanks a lot for the sponsors, and thank you.
Okay. Thanks, Professor David Zhang, your nice talk. Now a question and discussion time. So I have an open question. As we know, so that we can ICSD database. With about in your field, I don't know. There is open database in this field.
Yeah, it is an open database, and for decades, what we've been doing is we try to do measurements on real environments on the corrosion rate, on the corrosion of different materials, and we collect them back and put them in the catalog of databases, and we share them to the public, to the industries. So a part of our, a significant part of our databases are open to public.
Okay, okay. You mean that this database is
it's free.
Free.
It's free.
Okay, okay.
It's required by Ministry of Science and Technology, so we're evaluated by them, not by the number of publication, but actually by the quantity of data we share to the public.
Okay, okay. Thank you.
Professor Zhang, it's very nice talk. But I'm not familiar with your field, is corrosion. I think this very complicated the subject because of the interaction with the environment, the effect. So from now you get all kinds, so many time dependent of data, right? So in the future, what do you think about for our material design, which can directly relate to the this like such like a fatigue, corrosion resistant behavior of the materials? So we should go which direction in the future for us, because we do calculation of materials, right? And how to, from your research, give us some knowledge where to go.
Thank you, Brother Chen. I think it's a very important question for the community. As I said, corrosion is a different term compared to other physical chemical properties. It's really influenced by environmental conditions. So corrosion is not a simple materials property. It is a kind of interdisciplinary properties for materials, because it really can be influenced by the environmental. We have been calculated the importance of materials factor and environmental factor on corrosion. Actually, the importance of environmental parameters like can be 80% on the corrosion, and the 20% is the materials properties. So to design a material that lasts longer, or be stronger to corrosion processes, we need to have an understanding of the service condition that the materials will be used. And traditionally, this is not possible because we only have like pieces of really small fragmented data collected over years after years. But now with this kind of corrosion monitoring test, we can really know how the materials degrades and how the environmental factors will vary over time in a synchronized fashion. And also the sensors, the materials of the sensor can be really customized. So it's not just a carbon steel. It can be, for example, weathering steel. It can be stainless steel. It can be magnesium. It can be aluminum alloy. So the sensor itself can be really customized in terms of the materials composition and structures. So that also gives us power on inverse design of the materials based on the corrosion process, also based on the environmental variation. I think that's something that can be done in future.
Okay, thank you. I think it's a very important answer for us. Thank you.
Thanks very much for your speech. In speech, I saw the material TBS2. Do you think this material have a wide market? And is there any famous producer for such material in future?
Well, thank you for the question. I do believe there is a huge potential, commercialization potential for this type of material because the synthetic process is quite simple, and the composition actually not very complex, and cheap. So there is a big potential, I think, but it takes time because we'll need to do a lot of field measurements on different. It's a filler, and it can be incorporated into a lot of different standardized formulations of for the paints, but I think it's future efforts. It will takes time to do this kind of a massive outdoor exposure evaluation on this new material.
Okay, as far as I know, epoxy mostly used for metal, for steel. So TPS2 can join with, can use together with not only metal, maybe some other material
Oh, it's
which need anti-corrosion area.
yes, I think currently the coating we designed are mostly for metals, but we also work with other like ceramics or concretes, and I think it works similarly. Yeah.
Okay, thank you very much.
Okay, thanks. Let's have your nice talk because now time is up.